Hello everyone, my name is Chris Waid and this is my Lab 5 report for Summer Online Physics 2. In this lab, we will be exploring the interaction between a falling bar magnet and a tube of aluminum foil. Faraday's law relates time-varying magnetic field to a Curly electric field, whose path integral around a closed path is non-zero but provides an EMF that can drive current. This current in turn produces a magnetic field, which exerts a force on the source of the external magnetic field. In this experiment, the source of that external field will be a falling bar magnet, and the induced current is driven through a tube of aluminum foil. We will collect observational data from the magnet falling through the tube of aluminum foil, and then we will model this interaction computationally and compare our computational predictions to our observed data. In this lab, some of the key concepts we will cover are the Biot-Savart law to calculate the force exerted on the ring by the falling magnet, the Faraday's law to calculate the change in magnetic flux, as well as Newton's second and third laws. So here I've recorded my observations from the experiment. In the experiment, I used an aluminum foil tube that had a length of 0.27 meters and a thickness of aluminum that was 0.02 meters. The inner radius of my tube I measured to be 0.018 meters, and therefore the total radius is 0.038 meters. My mu value that I carried over from lab 3 was 1.44. And in my trial runs, I've recorded the time it took for the magnet to fall through each time and then calculated the average. You can see I got an average falling time of 1.232 seconds. I also followed the baseline code provided to create a computational model of this process. I created a function to calculate the magnetic field of the bar magnet shown in the image in the top, and then I created a function to calculate the magnetic flux, which is shown in the image on the bottom. The link to my GlowScript code will also be provided with my submission. Overall, my computational model produced this graph shown on the right that shows the velocity versus time of the magnet. And then the model also predicted a time that the magnet would take to fall through the tube, which in my case, the model predicted it to be 1.456 seconds. So now I'll answer some of the questions that were asked in the lab. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So this is an interesting question. If this were the case, the magnet would most likely take more time to fall through the tube because the induced currents would be increased. This reflects the truth behind Ohm's law and Faraday's law. In addition, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So I said that if holes were cut into the aluminum tube, the magnet would probably fall faster due to the decreasing magnetic force from the rings. Also, this change would decrease the magnitude of the induced magnetic fields overall. In conclusion, the observed time that it took for the magnet to fall through the tube was only slightly lower than what I predicted in my computational model. I experimented in the model and it seemed that the inner diameter of the tube played a large role in the expected time. If I increase the inner diameter of the tube, the magnet would fall through quicker according to the computational model, which makes sense. Also, in this lab, we proved that we can experimentally demonstrate Faraday's law, Lenz's law, and the Biot-Savart law, as we observed a bar magnet falling through a conductor. Thus, we also successfully developed a computational model to predict the falling behavior of the magnet under perfect conditions. Thank you for watching my presentation. I hope you have a great day.